Every winter morning, millions of drivers slide into freezing vehicles, crank the heat, and sit shivering in their driveways while the engine warms up. But deep inside that dark engine block, turning the key initiates a violent countdown. Every time you start a cold car, you have exactly 10 seconds for a highly specific fluid to bridge a gap smaller than a single human hair. If it fails, your engine begins to eat itself alive. The problem is gravity. Overnight, the vast majority of your motor oil drains out of the engine lock and down into the oil pan. When you turn the key, the engine operates with zero active oil pressure for a fraction of a second, leaving completely dry metal pistons and bearings to grind directly against each other. Drivers assume they are treating their expensive machinery with gentle respect. In reality, the simple act of a morning cold start subjects the engine's internal components to brutal physical wear before the car ever shifts out of park. When those metal components eventually fail, the financial damage skyrockets. If rod bearings inside a BMW 550i wear out from lack of lubrication, owners are handed an $11,000 invoice for a destroyed engine block. Pushing to the domestic tier, this exact breakdown forced Hyundai and Kia into a staggering $1.3 billion class action settlement. Premature rod bearing wear in over 4 million vehicles led to damaged rods literally puncturing engine blocks, sparking spontaneous non-collision fires. And physics scales up relentlessly. The National Transportation Safety Board has documented multiple general aviation flights where an identical lack of oil flow starved the crankshaft bearings, causing engines to completely seize mid-flight. Even the massive ocean vessel Maersk Eidenheim lost propulsion and dumped 260 shipping containers into the Pacific after its main engine bearings lost oil pressure. Whether it sits in a commuter driveway or powers an industrial cargo ship, the sequence is identical. A microscopic lack of lubrication dictates the total physical destruction of the machine. To understand how an engine systematically destroys itself, we have to look at how it normally survives. Imagine a heavy car speeding down a flooded highway, hitting a puddle and hydroplaning perfectly on top of the water. Engineers call this hydrodynamic lubrication. A spinning crankshaft acts as a fluid pump, pulling motor oil into a converging, pressurized wedge that physically lifts the metal shaft away from the bearing housing. This floating state requires roughly 36 pounds per square inch of oil feed pressure to generate enough upward force to completely counteract up to 15,737 pounds of downward physical load from the pistons. Take a single strand of human hair, slice it lengthwise into 100 perfectly equal pieces, and slide one sliver into that gap. That is your minimum oil film thickness. The operational gap separating these violently rotating components reaches as low as 0.5 microns. In the 1990s, engine builders used generous oil clearances, but modern corporate average fuel economy mandates forced manufacturers to hit aggressive new efficiency targets. To reduce drag, they shrank bearing clearances to microscopic levels and shifted entirely to ultra-thin, watery synthetic oils. You might think babying your car by letting it sit and idle in the driveway is saving this delicate system. In reality, science proves this exact habit is dragging your engine closer to the graveyard. Modern efficiency has stripped away the historical safety margins. Today's engines are incredibly powerful and clean, but they are entirely unforgiving of poor lubrication.
The most dangerous misconception everyday drivers hold is that waiting patiently for the dashboard temperature gauge to rise is the mechanically sympathetic approach to a winter morning. This chart tracks the exact conditions inside a cold engine during a 10-second startup. The data shows that cold oil is thick and sluggish, providing the worst possible conditions for fluid dynamics. Simply idling the engine fails to generate enough mechanical pressure to push that gel-like oil through the block, causing the boundary wear index to spike aggressively. Extended cold idling actively starves the machinery. A single cold start at 23 degrees Fahrenheit generates internal friction equivalent to driving 62 miles on the highway. The scientifically safest method is straightforward. Start the engine, wait exactly 30 seconds for baseline fluid circulation, and immediately drive away gently. This forces the oil pump to operate efficiently and rapidly pressurize the system. Attempting to baby a vehicle by letting it sit and idle is a complete misunderstanding of physics.
It actively accelerates metal destruction. Most mechanics will tell you that the easiest way to avoid oil starvation is to make sure your fluid is always fully topped up. But what happens when adding just a little bit too much oil triggers the exact same catastrophic failure? When you overfill the oil pan, the fluid level rises so high that it makes physical contact with the heavy counterweights on the rapidly spinning crankshaft. Think of a high-speed kitchen blender plunging into thick cream. The metal violently whips the excess oil at thousands of RPMs, injecting massive pockets of air into the fluid. Engineers call this aeration. The engine's oil pump is designed strictly to move liquid. It cannot pump or compress air. It sucks up this frothy foam and pushes it directly into the microscopic engine bearings. Because air compresses under pressure where liquid does not, the hydrodynamic wedge instantly collapses under the physical load of the pistons. The metal surfaces crash together just as violently as if the engine had zero oil inside it at all. Once that film collapses, the immense friction spot welds the bearing shell to the spinning crankshaft journal. The soft silver top layer is violently wiped away, exposing the dark copper beneath and ripping the shell completely out of its housing. Automotive engineers are clear. The safest position for your engine oil is exactly at the manufacturer's specification. Adding too much triggers the exact same $10,000 failure as running it bone dry. Protecting this incredibly tight 10-micron gap is strictly binary. You either maintain the hydrodynamic wedge or you buy a brand new engine. The first line of defense is upgrading your filtration. General Motors testing proved that moving from a standard 40-micron filter down to a high-efficiency 15-micron filter reduces engine wear by a massive 70%, safely trapping abrasive debris before it wedges into the bearing clearance. The second step is rigidly respecting your manufacturer's oil viscosity specifications. Never substitute a heavy 10W30 oil based on outdated logic if your manual mandates 0W20. The thicker oil physically cannot flow fast enough into modern clearances during a cold start, causing immediate boundary starvation. Finally, this lab report tracks the exact parts per million of wear metals suspended in your fluid. Submitting used oil for spectrographic analysis is the only way to catch a dangerous spike in lead and copper ratios before auditory knocking begins. Because by the time you hear a rhythmic ticking noise echoing from the block or discover sparkling metallic glitter on the end of your dipstick, the internal destruction is already permanent. A $10 premium oil filter and correct fluid levels are the absolute cheapest insurance policy you have against a catastrophic $10,000 failure.